let me try and stumble through this this problem. Some nice coffee. So we've got this machine component, T-shaped cross-section. We know that it's got an allowable compressive stress. Determine the largest force P that can be applied. Right. So my starting point is going to be working out the centroid, I suppose. So if we go back to the equations we got, we want to do the centroid. So here, if we're working with standard shapes, we can replace this with the sum of areas R divided by the sum of area. So obviously T-beam here, we're going to be using the standard shape, so and that will be the individual centroids locations for those particular shapes. I don't really know what subscript to do there. I could attempt to do Y. So I'm going to start off using that equation. So my centroid I'm dropping the subscripts for the problems. Right, so where are we? So we got this point here. So this is my shorter section from there to there. What's my radius? Why is that not obvious what the radius is? Oh, because I should be looking at this diagram. Okay. Right, so what we're going to have then, 80 times 20. So I've got 30 plus half of 20, so that's going to be 40. Next one is going to be a width of 20 times 40. And so we've got half of 40, which is 20, plus 20 and 30, so we've got 50 there. So I make that 70. Now I can just read off the areas. I know that I've done them first. So that's 80 times 20 plus 20 times 40. So at the very least I can find the centroid. Oh, that's a nice number, 50 millimeters. What to do next? Next thing is I'm going to do something a bit like a method of sections, cut this body and then expose the internal forces. So this is my applied force, P dash, and then it's going to expose an internal force, P, going in the opposite direction. And because these forces aren't aligned, that's going to create a turning moment, and we'll call that M. Okay, what next? Determine the largest force P that can, so I mean this is actually P dash, isn't it? That can be applied, although, okay, I can see, got P there. Okay. Rightio. So we're looking for stresses. We're going to combine both a direct stress and a bending stress. So I need an equation for a bending stress. So what we're going to use, know nothing about Young's modulus, so it's going to be this one here. So my stress is going to be a combination of P divided by A. If I let P to have a positive value, when I apply the load, I'm expecting this thing to get squashed, so we're, say, minus P. So we've got a compressive stress there. So if we've got a compressive stress, we are expecting the largest, actually, yeah, we've been, they're hinting at telling us to do this anyway. So we're expecting the largest stress to be compressive stress anyhow. And that's what we've been told to look for. So I now need to find an appropriate bending stress, but for a curved shape. So we're using this. Expression, and I need to make sure that this is going to give me a negative value. At the moment I'm not too sure whether it's going to be negative or positive, so I'll just add it on. Take away little r, take away big R. I'll put plus or minus there for the moment. A R bar Right. So we've found that. So obviously this tells us that we need to find area. That would be useful. So the area will be the sum of all these denominator terms here. So that's what? 80 times 20 plus 20 times 40. Okay, what else? I need to find my big R term. And that was... Well, here, I'm thinking there's two ways you can do it. You could do it the long way. Or you could look it up in a book. Since we're not actually told the values, let's do it the long way. So for rectangle sections, you can work them out and avoid having to do the integration. Since I don't have them to hand, I will not do it that way. So the first one is we'll integrate the bottom. So we start at here. So that will be a distance of 30. And then we're going to go up to here, so that'll be a distance of 50. The A, you can see that we can do nice cuts going in this direction. And I'll call that delta R direction. So the first bit will have a width of 80. And we're integrating. So the width bit is staying constant. And then we want to integrate from 50 up to 90. Its width is 20, delta R over R equals. So we got this all over 80 natural log 50 over 30 plus, it's no great hardship actually, is that 20 natural log 90 over 50. So the neutral axis is given as okay, I'm getting 45 for equations where I'm sort of like haven't finalized my answer. So I will then work to 5 significant figures, and I present final answers to 3 significant figures. That's my rule of thumb. So to 5 sig fig, that's 45.6. Okay, so if we compare that back to our centroid, what is this term here? So we've got a shape like this. The R bar is given as 50, so it's bang on here. That's where the R bar is. And the neutral axis is given a little bit below 45, so it's about here. So R bar, take away R, is a positive number. So this is positive. What does that mean? Positive if I take M to be positive, A is obviously positive. The compressive stress, so where are we looking for compression? I would guess we're looking for compression on this side. I'm pushing it in. Yeah, so the outer side is going into tension. So this is my location of interest. So R, this distance is, let's say, 30. 30 take away big R is going to be negative. And then R is going to be a positive number. So that means, if I've got this all correct, that should therefore be a positive. Because this term here should be negative. Okay. What next? What should I do next? I know what that term is. I know the A. What about M? So where is M behaving? it's behaving at the neutral axis. So coming back to this diagram here, where is that? So the neutral axis, although you don't agree with me. Okay, so I got that wrong. The M behaves at the centroid. Why would N behave at the centroid and not the neutral axis? Don't know. So this point here is the centroid. Forces are applied down the centroid, forces applied down neutral axis. Forces are applied down centroid, aren't they? Because otherwise that will create another turning moment. So okay, that is making sense. So my internal force here is I'm taking that to be going down the centroid, so not to create any more turning moment, and then that internal turning moment will be based around that location. So where is that in terms of my diagram? That's at 50 from here. So that's at this point here. So our M, we want to cast in terms of a P, and it's going to be this total distance from there to there. Okay. So I'm working in terms of values that I know how they should behave, whether they should be positive or not. So I'm taking my P here to be a positive value, although it's got a negative in front of it, to make sure this is compressive stress. This P, I want it to be positive because I was arguing that this M is going to be positive. So here the distance will be 60 plus 50. Yeah, so that's that total distance from there to there. So we have now got something which just has got P in it. So let's put our values in, and then we're almost done. So the stress, I've been working in millimeters. Is this going to cause me a problem? Right. This is very naughty of me, but I will carry on working in millimeters. Millimeters, Pascal, megapascals is equivalent to Newton millimeters squared. So I should be okay. So I'm going to put 50 in, minus P, which should give me a value in terms of newtons. divided by the area plus P 110 R little r is, we're expecting that to be on the inner side, so that's 30. Take away the neutral axis, okay, again this is the area, right, so that's going to give you a negative value. R bar, so the centroid is 50. And the little r is going to be 30. So we've got 1 divided by 24,000. It's interesting to see the size of the numbers. And here we've got 10 times 30, take away 45.608, divided by 2400 times 50, take away 45.608 times 30. So I just want to compare the direct stress and this bending stress. So here, a lot more bending stress going on than the direct stress. Would we guess that's the case? I guess so. So that leaves me with P is 50 divided by minus 5.8459, breaking my rule about sig fig. That should be 60. Times 10 to the minus 3. So that gives me minus 8.55. We'll leave it there because it's a final answer. Kilonewtons. Okay, so that agrees with Arnold. So, there we go. Bit of a struggle for me to get through that. First time I've done the problem like that.